Welcome to our discussion on Monte Carlo tree search. As mentioned in our previous lecture on search algorithms where we covered depth first, breadth first, uniform cost, greedy, and A-star searches, today we'll explore how a special variant of the Monte Carlo tree search algorithm, in short, MCTS, can help us find the best route from Milan to Naples in Italy. The Monte Carlo method is known among others for its use of random sampling to solve problems that are difficult, or even impossible to tackle with other approaches. Where MCTS shines, is its ability to work effectively even when whole chunks of information are missing from the data. To illustrate this for our case, we will introduce several unknown distances between cities, and see how the Monte Carlo method overcomes this. To the right of the image on the screen is a reminder of our mission. We need to deliver a parcel from Milan to Naples, and are looking for the shortest route. In our previous tree search video, we had available to us all the road distances between cities. For the informed search types, greedy and A-star, we also had a map at our disposal. To the left of the screen is the list of the distances as they appear in the Python code. Now, imagine that not only do we not have a map, we are also lacking information on all the road distances beyond Pisa and Pescara. Note that even for MCTS, this is a much tougher constraint than just eliminating information here and there in the tree, where parallel routes can provide some insight to the missing information. And again, none of the methods discussed in our previous video would have been able to find the best route in this situation, or for that matter, any route at all. Now, there are several variants of the Monte Carlo method. The one that has received most of the attention recently is the game-playing algorithm, which has earned its fame by helping beating the world champion of the game Go in 2016. But before we dive into our route optimization problem, let's briefly review the four main steps of Monte Carlo tree search. As we can see here, MCTS works through an iterative process of selection, expansion, rollout, and backpropagation. Selection is the first step, where we choose which branch of the tree to explore. In many cases it is our currently selected node. In expansion, we add new branches for exploring our search tree. Rollout continues through the tree via random selection of branches, all the way to the end. This, by the way, is very efficient in terms of computational resources because no calculations are involved. What we are looking for here is merely routes that get us all the way to our target. After many such attempts, we will have some idea, although no more than an estimate, of our best course of action going forward from the node we are at. Finally, in backpropagation, we calculate that estimate in terms of probability of reaching our goal. This probability is essentially the value of each of our choices, based on the outcome of the rollout. This was definitely a very short coverage of the Monte Carlo method, and we plan to expand the discussion of this method in future videos. That said, the purpose of the current presentation is to simply demonstrate the method on the Milan to Naples tree search, to see how powerful it is. For anyone already interested in a deeper understanding of the method, there is a multitude of literature and videos on the web. Wikipedia itself has a good overview, which is strongly recommended. So let us now have a closer look at our specific algorithm, in the context of route optimization. We start by initializing estimates for our unknown distances. These can be arbitrary, or random numbers, or for example the average of the distances known to us. In our case this comes out as 138 kilometers. This probably makes more sense in our case than just starting with an arbitrary or random number. The next step is to start our main iterative process. In each iteration, we will perform a full route simulation, running all the combinations that would get us from Milan to Naples. But we will not simply add the distances. Instead, we will divide the route distance by our nominal driving speed, let's say 80 km per hour, and then add to each segment of the journey some variability or jitter, to simulate real-world, varying traffic conditions. We repeat these simulations for all the possible routes numerous times, until the statistical variance is below a defined threshold. This process is shown in the calculate travel time inner loop. After collecting enough samples to ensure statistical reliability, we calculate what we call coherence. Coherence is the mathematical compass guiding our entire approach, and we will explain it in more detail in a minute. In the meantime, let us just mention that as long as coherence improves, we will continue to update our distance estimates. We will stop when we reach convergence, either by hitting our iteration limit, or when our coherence score reaches a plateau, and has stopped improving from one cycle to the next. The key insight is, that through this repeated process of simulation and coherence optimization, the Monte Carlo method is able to simultaneously discover, both the optimal route, and the true values of the missing distances. This unique ability sets it aside from the other tree search methods. So what is coherence? Mathematically speaking, it is the summation, for all the routes, of the ratio between the simulated distances for each route, to its simple algebraic addition of its segment distances. Here, routes that have segments with unknown distances, or rather, the arbitrarily estimated distance, will behave differently than the fully informed routes. And the larger the errors are in the route's estimated segment, the more noticeable will the difference be in the simulation versus expectation ratio, between these routes and other routes that have less or no internal errors. So on the flowchart, in the outer loop termed calculate coherence, the algorithm will normally prefer solutions that minimize the differences in the simulation versus expectation ratio between the routes, thereby increasing coherence. As long as coherence is improving, we continue updating the distance estimates. It has been shown that these updates will slowly move the initial estimated distances towards their true values. The outermost loop in the program's flowchart keeps the iterations going until some predetermined number has been reached, or before that, if the correlation has plateaued, meaning that there is no significant improvement in the overall coherence between the various possible routes. Here is a glance into the operation of the code that executes the program, as per the previous flowchart. In this specific run, the total predefined number of iterations was set to 6,000. For our Naples to Milan example, a typical run takes less than 1 minute on an Apple M4 processor. The image shows a screenshot of the output console, taken shortly after the run has started, with some 100 iterations already behind us. On the left, we see graphs of our route travel time estimates, as the algorithm runs through its iterations. Each colored line represents a different possible route from Milan to Naples. A legend is shown below the graphs. The upper right window shows the development of the coherence score. As the algorithm progresses, this score decreases, indicating that our distance estimates are becoming more consistent across all routes. We can also see that directly on the bottom right graphs, where the missing distance estimates are evolving throughout the optimization process. Note that we started at t=0 with no knowledge of these distances. Instead, we assigned all of them the average distance of 138 kilometers. Still, it doesn't take more than a few iterations for the estimated distances to start moving away from the arbitrary number, and toward each segment's own correct value. Let us now continue the run. The run has reached 6,000 iterations, and here are our main results. The algorithm has determined that the best route from Milan to Naples passes through Genoa, Pisa, Rome, and Naples. The average travel time is reported as 9.07 hours. The reliability score of 0.94 at the top right indicates high confidence in this route, showing that it consistently performed well across different traffic scenarios. The algorithm calculated the total distance of this optimal route to a total of 716 kilometers. This is close to the values that were achieved using the other tree search methods, which we covered in our previous Milan to Naples video. Below, and to the right of the printed summary, is again the last plot that we received on this run for the travel time estimates. It is interesting to note that as the simulation progressed, those 7 routes that had segments with missing data, increased overall in travel time relative to the initial estimate. For the shortest route, the difference ended up as much as 2.5 hours. We will see in a minute where this number comes from. Now, let us look at our algorithm's estimated distances, relative to the actual values, which as you may recall, we have not disclosed to the program. These are now being exposed in the code block on the right. Let's also place a copy of the numbers next to the simulated results. As you can see, while there are variations in the individual estimates, many are surprisingly close to the actual values. What shows a surprisingly close, almost 100% perfect correlation, is the sum of all these initially unknown segment lengths. Looking now once again at the best route found by the algorithm, remember it had two unknown segments. The first one was Pisa-Rome, which was estimated by the algorithm to be 270 kilometers, which is within 7% of the true missing segment length. The second, Rome to Naples segment, came to within 3% of the true number. If we calculate the differences to the initial estimates of 138 kilometers for both segments, and divide by the nominal driving speed, here's our 2.5 hours difference that we saw earlier in the route travel time graphs. In conclusion, our Monte Carlo implementation has demonstrated three powerful capabilities. It found the optimal route from Milan to Naples despite having incomplete information. It estimated unknown distances with reasonable accuracy. And it captured the overall structure of Italy's road network with remarkable precision. The two key features that enabled this success were the law of large numbers, allowing us to build statistical confidence through thousands of simulations, and coherence, which enabled us to discover consistent relationships between routes. This is why the Monte Carlo tree search and general simulation algorithms are regarded today as some of the most powerful AI methods for searching through domains that have limited data. In that regard, the Monte Carlo method offers an excellent emulation of human and animal intuition.